Welcome back to this module on an introduction to optimal decision making. In this section, we will focus on multi-class scenario. Then, as we have seen in the previous sections, with the binary problems, we had a binary matrix with 2 columns and 2 rows. And basically, for the multi-class case, we can extend this cost matrix with k columns and k rows, basically. However, if in the binary case we could find a threshold, an optimal threshold, which was a value, in this multi-class setting, this is not the case anymore. We will have a decision boundary, or multiple decision boundaries that will live in the simplex, in the probability simplex. In order to illustrate that, we will look at a ternary example. Then this is just another example in which the diagonal are all gains and the non-diagonal elements are all cost for 3 classes. And as we have done before, let's imagine that we have a new instance with those posterior probabilities 0, 5, 0, 1 and 0, 4 for class 1, class 2 and class 3. And we can, as we have done before, calculate what is the expected cost of making each of those 3 predictions. Then, as we did in the previous sections, we can compute those, and in this case, the optimal decision will be to select to predict class 3, which has an expected cost of -15, which is an actual gain. And how can we visualize the cost lines that we have seen in the previous sections? In the ternary case, then we cannot visualize them as simple lines. In this case, are isolines in a simplex, living in a simplex. Then let's focus on the first one. Will show only the expected cost of predicting class 1. Predicting class 1 corresponds to this column, and this -10 is the cost that we will have if we predict class 1 when the true class is class 1, and this corresponds to the posterior probability of class 1 given x being 1, given that we are predicting class 1. Well, yeah, this is basically this value, -10. Similarly, for column 2, the lowest cost will correspond to this boundary. In this part of the simplex is basically the posterior probability of class 2 given x is the highest, is 1. And finally, for class 3, this one is this -90, as we can see. The rest of the corners correspond to the rest of the matrix. For example, let's look at the highest cost of predicting class 3, which is if the true class is class 2 is 60, which corresponds to this corner here with a value of 60. Then what are the optimal decisions in this case? In this case, I don't have here a closed form solution, but I have computed every single cost basically in a grid on the probability simplex, and then if I show the color in green, it's because the class 3 had the minimum cost, expected cost basically, which can be seen here, for example, with the minimum cost being, if we predict class 3 and it is actually class 3, the cost is -90, which is a gain. And then we can do the same with all of them, and we can imagine here that there is a decision boundary here, here, and here that is determining which is the combination of probabilities that makes an optimal decision in one side or the other. And then this is not a ternary problem, but it is similar. what happens if we have the option of abstaining? What we are doing is basically adding an additional column into this cost matrix. Basically, what will happen if we make the decision of predicting class 1, the decision of predicting class 2, or the decision of abstaining? And abstaining, someone else may have, maybe there is an additional test that someone can run, and then this may be the cost that will be involved if we abstain. Then, as we have done before, now we can estimate the expected cost of predicting class 1, the class 2, and what is the expected cost of abstaining. In the case of the abstention, in this case, because both possibilities are the same value, the expected cost will actually be that value. And then in this particular case, the smallest cost will be predicting class 2. And how does this look in the cost lines figure? Basically, we have, as in the binary case in the past, we have two lines, one for class 1, and this is, class 1, and one for class 2, and now we have an additional one line that is for the abstention. We can see that the optimal decision is to select these costs, which are the lower envelope of all of these cost lines. And this is an additional example showing that the cost of abstention may not be the same for one class or the other, and then this is just translated in a different cost line for the abstention, but still we can see where is the lower envelope, which determines the optimal decisions basically.